Okay. Well, I gave on purpose a title quite a bit generic, but okay, I didn't want to make a talk only on the, let's say, latest results, but I would have liked to make some kind of summary of some parts of my research activity in which Claudio was actively involved. And I have to say that my first acquaintance with Claudio was, I think, in the late 80s, when we were both both PhD students, as far as I remember. Then, okay, we, let's say, kept constantly in contact, maybe not with a very, very high rate, but with, let's say, some constant rate. And well, I had the pleasure to collaborate with him in, well, let's say, on some topics in Hamiltonian mechanics, where Claudio was involved, especially for his expertise in geometry of this of all this stuff. And that was on starting from 2003 to 2004 for some some years. I would say, okay, lately I started doing something more with more physical application, and also, well, obviously I couldn't catch Claudio in his multifaceted activities, especially in those related with how it's called, dissemination of science. But I have to say that sometimes in bookshops and libraries, I remarked his name coming out from the first, I mean, from the windows, and that was a pleasure. And obviously, I have to say that it was a pleasure to interact and know Claudio. I still remember one Branzino al Sale when Dubrovin was there. Was I would say. Okay, so the talk now. Okay, I have to do this. Okay, I would say that there are two. Talk is roughly speaking divided in two. The first, I will speak about some results of which were obtained by in collaboration with Claudio, and even if they are not so recent, but I think that they have some merit to be remembered. And obviously Claudio and other people, a couple of which are here, especially Marco Pedroni. And then I will speak about some more recent results obtained in another collaboration, and which have something to do with as I said, more physical or concrete applications, which are basically Euler equations. But you shall see that I hope that there is a common fil rouge in all these activities. Sorry, let's do it this way. Well, let me remind the less expert that, okay, what is an integrable system? Basically, it's a system which has is a Hamiltonian system, which has the Liouville property, that is that you have a phase space, which is a 2n-dimensional symplectic manifold with symplectic form omega, and you have an Hamiltonian, which dictates the time evolution. And the usual definition, I'm sorry for starting right from the scratch, I would say, of integrability, if you have, is that a system is integrable if you have a number n equal to the number of degrees of freedom of mutually commuting and functionally independent integrals of the motion. Poisson bracket is defined in this way up to a sign, which is always, it depends on convention, schools, and people, and so on and so forth. But since 0 is equal to minus 0, this is okay. And the general remark is that usually these integrals of motion, which everybody who deals with mechanical problem knows they are a gift of God in some sense, are associated with three kinds of somehow linked, but roughly speaking, different properties. One is symmetries, that is Lie group action on the phase space. The other one is related with some iterative structures, which I have in mind, especially the Hamiltonian structures, sorry for the misprint, or something I would call some inherited structures, some something like, well, for instance, you take a simple system with a non-trivial constraint or some G action, and you get some Dirac type reduction, which gives rise to a non-trivial system. Okay, the Neumann system is, and also the Calogero system, of which I would briefly speak later, are two examples of this. So I hope you understand what I wrote. Dira is Dirac, but okay. Well, in general, just to place things in a way that maybe more people can understand. Okay, the first item leads to the so-called Marsden-Weinstein reduction, which has the counterpart in soliton theory with the Drinfeld-Sokolov theory of generalized KdV equation. Okay, this is known as Hamiltonian system with G symmetries. The item 2 basically was introduced in the KdV theory by Magri and led to the concept of Lenard-Magri sequence. And here I hope that Boris Konopelchenko is not participating in this conference. Marco knows why. And actually, my work with Claudio and other collaborators, basically Marco Pedroni, Giovanni Ortensi, and Igor Mencattini, focused on some aspects of the second two. And okay, basically, for what 2 and 3 are concerned, there is the Neumann problem, the Neumann system. This is well known. And well, this is a typical example of a very simple system which acquires non-triviality when you reduce it. That is, if you consider on the usual cotangent space to R n plus 1, where maybe since I added this G and this 1 over xi squared, I should have stripped off the zeros, but that's not really relevant. You consider this Hamiltonian, which is okay, the system with n plus 1 particles. You have this deformed harmonic oscillator, deformed by the presence of this repulsive term, but you could set also the G equal to 0. This is the Rosocatius part that's not really relevant. And you have this system on n plus 1 modified harmonic oscillators, which are uncoupled. And this is trivially integrable because if you call HK the Hamiltonian of the single particle, this is, okay, this family provides the complete set of integrals of the motion. What one can do is, as in the true Neumann system, or non-Rosocatius, you can restrict the spatial coordinates, let me call it this way, x, y are the momenta. So you restrict the x coordinates to be on the unit sphere in Rn plus 1. And the system is much less trivial. However, it was shown, well, in the case n equal 3 by Neumann in the 19th century, as far as I remember, that the system is integrable. And then the general case was proved to be integral much more recently in the 60s or 70s by using the Lax representation. What we did is framing into the iterative scheme in the sense that we proved and constructed that along with the natural symplectic structure of on the cotangent bundle of the unit sphere in Rn+1, there is a recursion operator. I won't give here the precise definitions. I can refer to the talk by Marco Pedroni a couple of days ago. Basically, we have a torsionless 1-1 tensor, which is in some sense compatible, that acting on the first Hamiltonian generates by recursion, and the recursion is here. It's kind of modified Leonard-Magri recursion, mutually commuting Hamiltonians, and also provides separation coordinates for the Hamilton-Jacobi equation via its diagonalization. Another instance was the rational Calogero-Moser model. This is a much more recent system, and it was proved in the late 60s or 70s to be integrable by Calogero and Marchioro. Incidentally, there is a strange history because I mean they first, let's say, diagonalized the quantum Hamiltonian and then realized that their diagonalization was related to the integrability of the classical counterpart of this system. Okay, what is this system? Let me start from the bottom. I mean, physically, it is a system of n particles on the line interacting with inverse square potential, depending on the relative distances of particles. And for its integrability, one sees that it admits a Lax representation. The Lax representation is written here. I only wrote the important part of the Lax pair. This is this matrix cell. And later, I would say by Moser, but I'm afraid I will be a bit sloppy with historical remarks and quotations also. It was realized by some people, okay, that the Calogero-Moser system could be obtained by considering a system of n square identical free particles moving on the line, whose coordinates and momenta could be encoded in a pair of n times n matrices, by Hamiltonian reduction, considering the conjugation action of the general linear group, and fixing the momentum mapping to be the identity minus rank 1 matrix. And so basically this fits in the point I, as I said, because the classical approach to the rational Calogero model is by means of, is a classical example of a Hamiltonian system admitting G symmetry. And what we did was to consider its bi-Hamiltonian geometry of this. The bi-Hamiltonian geometry of this model, I mean of the reduced model, was found by Magri and Marsico in 1906, who showed that if one defines, along with the traces of the along with the mutually commuting Hamiltonian, which are the traces, sorry, there is a mismatch of the indices, this should be a K, the traces of the powers of the Lax matrix, one could define n more coordinates, which are traces of some powers of the L matrix times the diagonal matrix, which has the position on the of the particles on the diagonal, and okay, the definition of the two Poisson structures. Now this I should read K is this one. They are not very interesting in themselves. Actually, they are linear. They are linear Poisson brackets. Both the first Poisson bracket and the second one. And okay, the natural question was to ask where did this Hamilton structures come from? And okay, we proved that also this could be obtained as a reduction from a quite general Poisson pair living on cotangent bundles. In particular, in this case, the cotangent bundle is the product, the Cartesian product of pairs of matrices, because it's the cotangent bundle of the algebra mathrack GLN. And in particular, the first structure comes from the standard Poisson structure on a cotangent bundle, while the first one is associated with a semi-direct product of GLN with itself. Okay, and the bi-Hamiltonian structure of Magre and Marsico, you see that the bi-Hamiltonian structure of the rational Calogero model is associated with a couple of projections. And the first one is a projection with respect to the joint action of the group GLN on the cotangent bundle of the Isely algebra. And the second one is a projection on a 2n-dimensional manifold parameterized by these 2n functions, which form a closed algebra under the Poisson brackets, and so define a P-Poisson manifold. Okay, this was the first result. Later, we also discussed within the framework of what are called omega n manifolds, we proved a formula by Sklianin, who observed that in some small n cases was a very nice formula for the conjugated momenta to the eigenvalues of the Lax matrices, which is this one. Okay, this formula admits a very, very natural formulation inside the let me call it the bi-Hamiltonian approach to integrable systems. Okay, and so far for the first part, but I want to stress that these results have a common conceptual root, that is Hamiltonian structures and their geometric reduction. And the same idea is providing the leading ideas of the second part, which is devoted to the integrable or near to integrable PDEs originating from fluid dynamics. I'm not speaking about very abstract or exotic model. I'm speaking about some instances in the theory of Euler fluids, but I would like to remember that there is some merit, because you know, the history of integrable system is not very linear one, in the sense that at the end of the 19th century, with the work of Jacobi, Staker, and other people, there was a tendency to think that integrable system could provide a paradigm for mechanical programs. Then Poincaré showed that this is not true by proving the non-existence of further integrals of the motion in the three-body Kepler problem. And so the theory of integrable system, let's say, had some 3 or 4 decades of, well, let's say living underground, let's say it was kind of an underdog theory, if we can paraphrase our prime minister. But in the 50s, it came with some arrogance out with the works of Kraskal and Zabusky and the discovery of the integrability of KDV. And in particular, in the sequel of this talk, I will try and apply these ideas to some, to a special, but it is physically relevant class of fluid motion, the one of the stratified fluid flows. Now, since I don't think this is very common to you, I mean, this notion, I will show you a movie of an experiment which was not done in Brookhaven, neither in CERN.
The experiment is to show us the movie.
Come on, come on. Sorry, I have to. Now let me show the movie, because I have to share again. And now I share this. Now it's a photograph, but soon enough it will become a movie. Well, and the idea is that, so let me show the movie. You have a tank, and you start filling it with some salted water, which is the blue water. And then you pour over it in a very, very delicate way, let's say so, some fresh water, which is the transparent water. And I hope you see, because I have this, I mean, there is a movable slab. You create a theta function, then you remove, okay, this unfortunately the movie is not going very well, but I hope you can see, even if it is framed, but the movie is continuous. You can find it on the internet. This this wave, this internal wave propagating as a wave, describing the interface between the two fluid. And something I would like to draw your attention on, because it is important in the mathematical setting for these theories, is that the upper boundary between fresh water and air is not moving at all. And indeed, in the mathematical model, we will pretend that there is a rigid lid between, I mean, on top of that. So let me share again the mathematics. Okay. Now, I mean, in mathematical terms, this is an heterogeneous, uncompressible fluid flow, Euler, which means that the velocity vector field, which I take right from the scratch in 2 dimensions, is solenoidal. And so the divergenceless. Now the density is not a constant, but thanks to incompressibility, it satisfies this advection or convection equation. I mean, the rho t plus v dot prod, the grad of rho is equal to 0. And then Euler means simply that, well, the external force is the the gravity is gravity, and the internal stresses are just due to the pressure. Okay. We shall be interested in the case in which we shall have a sharp stratification, in the sense that we have, as we managed with, well, as we did in the experiment, you have a system of two fluid, both they are confined below and on top. And inside the bulk, we have constant densities. And then the problem is to describe how the interface evolves and how the velocity evolves. Okay, which velocity? Well, we shall see, because, okay, look, here we have a spatial 2D system. We want to drop on a spatial one-dimensional system in an Hamiltonian way. How can we do that? Well, you look at the literature, and actually in 1986, Benjamin described in a bit complicated way the theory, the Hamiltonian representation for Euler fluids in such instances. This, well, of course, he considered a generic 2D stratification, and he introduced along as a basic variable, I mean, he had the density, and he introduced this, it's called density momentum vorticity, as the curve of the momentum, basically, not as usually in this in the theory of incompressible flows. The expert know that they admit a formulation in terms of the vorticity, which is the curl of the velocity. Introduce this, okay, with some notations. It said that if you define very naturally the Hamiltonian to be the sum of the kinetic and potential energy. It first managed to write the equation in this strange form, but then he realized that actually the resulting Euler equation for these two variables were a Hamiltonian set of equations, where the Hamiltonian structure is quite natural, it's just easily theoretical. Okay. Now, what can one think when dealing with sharply stratified flows? Well, basically, sharply stratified flows are a tiny subset of general stratified configuration. So basically, you have that you can parameterize the density as a function of x and z in this way by using a generalized function, and the speed in the same way. You get inside this picture, you see the interface between the two fluids, which the motion of which is one would like to describe. Now, if we perform this very simple averaging process, that is, we integrate over the height of the channel, which is fixed, I mean, it is as 0 in the h. What we get is this expression. That is the average of the vorticity, assuming that the fluid is irrotational in the bulk of each layer, is given by this expression, which is basically the tangential momentum shear at the at the interface. But here you see you have a function of only one variable. If you integrate the density, basically you get simply, and you divide by ρ2 minus ρ1, you have simply the 8 of the interface between the two layers. Okay, and sorry, this is what one can do is to try and compute the reduced Poisson tensor. Okay, by means of a standard procedure is okay, so-called Marsden-Weinstein procedure, but basically you do what? You have a manifold of your fields of interest, which are the 8 of the of the interface, and this averaged vorticity, quotation mark, and you take a one form here, you pull it back to the big manifold, then you compute the Poisson tensor on the big manifold on such one forms, and then you push it back. Okay, the first step is here, very simple. You take the second step gives you this strange object, then you integrate once again, and simply you get that the Poisson tensor is very, very simple. This is a bit strange because usually when you reduce Poisson tensors, you get some more complicated Poisson tensors than you started from, for instance, in Neumann, but also in Calogero and so on and so forth. But here you start from a linear Poisson tensor and get to the constant one. This should be represented by anti-diagonal matrices with derivatives.
Greg, yes? A very quick question. Which is the symmetry group acting in this case? Because if you have a
here it is the third kind of thing. I didn't well, we didn't think about a symmetry group, but you have a submanifold of a manifold. Then you can define a suitable distribution in the sense, sorry, the deltas are generalized function. I mean, distribution in the geometric sense, and the Marsden-Weinstein and Marsden ratio, I would say, theory of reductions applies in this case.
Okay, thanks.
So there is no symmetry group. The approach you are mentioning is the one which was pursued by Olm and collaborators, but at a certain moment they cheated quite in doing. Okay, maybe if I have time, I'll make a remark on this. And okay, as I said before, the reduced tensor is this one. And the pair of variables we identified before is a pair of canonical structure. Sorry, canonical coordinates. Now, let me move a bit far because I would like to go to the core without having to rush. Well, the point is that, okay, you have a Poisson manifold. What now you have to do is to reduce is to find the Hamiltonian, okay? And I repeat here the picture, and okay, what you have to do is basically is to write under suitable asymptotic expansions the energy of the fluid. The problem is that the energy of the fluid in the 2D case depends also on vertical velocities. So you need some asymptotic expansion to express asymptotically the vertical velocity in terms of your variables. This can be done. I will spare the details. This is somehow standard things. Computations are a bit nasty. And okay, the idea is, okay, the point with respect to Ohm is that, I mean, they make the assumption that nothing depends on Z, but this is not true, because if you switch in just a little bit of dispersion, you see that this is not true. But I mean, I don't want to get into trouble with Daryl Holm, which is a very good guy. Now, okay, the idea is that you first express everything in terms, you have to expand the velocities, and then you have two constraints. And so you can express everything in terms of the speed and the variable, sorry, not the speed, the interface 8 and the variable sigma. Cutting a long story very, very short. This is not short, sorry. You get this intermediate expression, and then you have to choose which asymptotic to do. And we placed, let's say, a specific relation between dispersion and nonlinearity, saying that along with the dispersion parameter, which is epsilon, which is the duration of the eighth of the channel and the typical wave amplitude L, there is also this small amplitude parameter, and we baptize mildly nonlinear case, defined by some scaling in which alpha is much smaller than epsilon, but much bigger than epsilon squared, which basically means that we shall keep terms of order epsilon squared, epsilon squared, alpha, and alpha squared, and discard everything else. The usual, for those who have already heard of it, weakly nonlinear approximation, to which I shall return on at the end, is saying that alpha scales as epsilon squared. Okay. Now, there are some consequences of this, but the important one is that at the end of the Hamiltonian density acquires this very, very simple form, because it is, okay, made of a quadratic part, sigma squared plus zeta squared, a cubic part, zeta sigma squared, a fourth order part, and a dispersive part, which is sigma xx, or if you prefer, minus a k epsilon squared k sigma x squared. Now, the relation between these symbolic parameters and the parameters of the theory, which are the two densities, and H1 and H2 are two asymptotic aids of the fluid, are this one, but they are not very important. You make another non-dimensionalization, and finally you get this system of equation, which is a system of equation in conservation law form. So it has some kind of interesting properties. Which are the interesting properties? That, first of all, okay, you can linearize system, and you see that as usual in these theories, when you have waves propagating in two directions, and you make an expansion in the dispersion parameter, you have some troubles at these troubles at big K's, but K's is the wave number, so it is the inverse of the wavelength. So since we are making a kind of long wave expansion, this is okay. Then you can study traveling waves, and this is very standard. Well, basically, at the end of the day, just in the case of KdV, you have to study the analog of a particle moving in a suitable potential, and well, you have some results. But what I wanted to present is the following: is that okay, this system is not integrable. I will come in the last 5 minutes to its integrable friend, let's say so. And but there is a full qualitative agreement with the fully nonlinear theory. Remember, we just retained a moderate amount of nonlinearity. Say we inserted nonlinearity and dispersion cum cohesio. But qualitatively, we have agreement with the analytical result in Grignardi models, which in turn have well, have a very good agreement with the Euler experiments. This is the profile for an internal solitary wave, you see. And also, this is some parameters, which is called effective wavelength, which signals the following thing. Okay, this, you see that the behavior is similar. In particular here, this new asymptote is related with the fact that Euler equation admits solutions which are not only solitons, like in the KdV case, but are, let's say, front solutions, which in the potential are associated with the heteroclinic orbits. This is a feature which KdV does not have. But how to go to KdV from here? Well, I will skip this. Well, it is well known that KdV is obtained by what I skipped before, the Boussinesq system, or from the water wave model, by making a unidirectionality assumption. Well, that is, you seek for waves, nonlinear waves propagating, let's say, to the right. And I mean, the standard technique to do this is that you seek for a relation between the two variables, which are sigma and theta. You guess this form in such a way that asymptotically these two equations are one and the same equation. So they are consistent, and well, you can do the exercise in this way. For instance, the way I'm describing is the way in which, if you look at Witham's book, Linear and Nonlinear Waves, the KdV equation is determined. Okay, this is a kind of exercise you can do. The link is written here. You see, it's a nonlinear and dispersive link. And well, the unidirectional model is what is called the Garnier equation, which is an equation which mixes, in some sense, for the expert, KdV and modified KdV. Because, I mean, if you drop this term, you see you get KdV. If you drop this, you get modified KdV with this interaction. The dispersive case is the same. Now, what has to do with Hamiltonian? Well, the idea is the following. You consider the equation you got before as the link to obtain from the two-dimensional system an equation for waves propagating in the towards right plus infinity, let me say so. And you consider this as an asymptotic, as a constraint, okay, between the two variables. When you have a constraint, you apply Dirac reduction. Okay, you check everything is fine. The problem is that you have to, in doing Dirac reduction in the finite dimensional case, you have to invert the matrix of the Poisson bracket of the constraints. Here you have to invert a differential operator, but we are in an asymptotic regime, so the inversion of this operator can be computed. Okay, it's complicated. You compute the Poisson tensor, and you see that everything is fine, in the sense that you have a Poisson, an asymptotic Poisson structure, which gives you the correct unidirectional model equations. But the final point is the following. Okay, the Poisson, the Dirac-reduced Poisson tensor as a third derivative, this very well-known term, plus this nasty term, which is of order alpha squared. Okay, so if you forget the mildly nonlinearity, which for some reason is important, and you go in the weakly nonlinear asymptotics, simply you get that the Dirac-reduced Poisson tensor yields the Magri-Poisson pencil for KdV, in which the physically nice thing is that this abstract pencil parameter by Magri is nothing but the inverse of the small dispersion parameter. And I think I've run out of my time. I thank you for the attention and wish the best and happy and fruitful future for Claudio.
Thank you, Greg. Thank you very much for your talk.
Thank you for listening.
Are there any questions for Greg?
So thank you, Greg, for a very nice talk. So, so if I understood correctly, starting from a quite physical situation, you can recover Magri's description for the KdV in some sense, at least asymptotically.
Asymptotic, yes, you got the message. Well, this is a joint work with Roberto Camassa and Marco Pedroni, Giovanni Ortenzi, and a student of mine. Yes, and okay, it is a double process of reduction because you start from a very physical instance, which is an Hamiltonian structure for stratified flows. You make a big reduction in the sense that you pass from fields with in 2D, in two spatial dimensions, to a couple of fields in one spatial dimension. I mean, this is known. And then by means of a further reduction, you get the Magri structure. It is fair to say that some ideas in this direction were set forth by Olver in 85 or something like that. But it is also fair to say that he hadn't, well, quite oddly, because he's an expert in differential geometry, he hadn't really grasped the necessity to, that when you have a submanifold, I mean, you don't, the reduction is Dirac reduction, not.
Well, because essentially it's the same as, I mean, having a, I don't know, kind of a subalgebra is having a constraint is the same, more or less.
Yes.
More or less.
Okay, but yes, the final message is this one. I mean, in some sense, Magri structure is not, well, of course, it was discovered by the ingenuity of Franco, okay? But in some sense, it has some asymptotical physical origin, let's say so, and geometric origin from a very natural structure. Okay.
Very nice. Very astute and nice.
Sorry?
Astute and nice.
I got it.
Any more questions? Apparently not. So thanks again, Greg.
Thank you for listening. Now I stop sharing.
Yeah.
Okay.